So let's continue looking at power ratings for resistors. Look at some example problems based on a circuit. So we're going to choose an adequate power rating for each of the metal film resistors, okay? An 1/8 watt, a 1/4 watt, a 1/2 watt, and a 1 watt. Okay, so you have to imagine these things in sizes. You know, a 1 watt resistor is going to be a pretty good size barrel on that resistor, where an 1/8 watt is going to be fairly small, fairly tiny. So we've got circuit A that has a 10 volt source and a 120 ohm resistor. Circuit B has a 10 milliamp current and a 1000 ohm resistor. So in the first circuit then, circuit A, the actual power is V squared times R, because we know V and we know R. So 10 volts squared gives us 100 and gives us 100 volts squared and 120 ohms of resistance. So we divide 120 ohms into 100 volts squared and we get 0.833 watts. So we need to select a resistor with a power rating higher than the actual power, because you don't want to rate it too low because it'll burn up. So you want to make sure you've got a margin there. So in this case, a 1 watt resistor should be used. So in 47B, the actual power is I squared R. So in this case, 10 milliamps squared, 1000 ohms, gives us a 1/10 watt resistor. So if we look at the small one here, a 1/8 watt, which is 0.125, and we're looking at 0.1, an 1/8 watt resistor gives us plenty of margin. Okay, so you always calculate a little higher for the value. So 0.883 in the first one, 1 watt resistor. 0.1, we calculate, we need a 0.125 resistor. When the power in a resistor is greater than its rating, the resistor will become excessively hot. I mean, you will burn yourself if you touch it. Typically, when you open up a circuit board, if something is going wrong, you will see the resistor burnt to a crisp. As a result, the resistor may burn open, or its resistance value may change, depending on, if it's been heating up over time. A resistor that's been damaged because of overheating can often be detected by charred or altered appearance of its surface. Also, you will smell it. If there's no visual evidence, a resistor that is suspected of being damaged can be checked with an ohm meter for an open or incorrect resistance value. Remember, that has to be removed from the circuit, though, to do that. You cannot check resistors in the circuit. Recall that one or both leads of the resistor should be removed from a circuit to measure the resistance. In checking a resistor with an ohm meter, a couple examples here. You'll have different ones in your labs. A typical digital multimeter and an analog multimeter, here's your digital one, here's your analog one, are shown. For the digital meter, you use the round function switch in the ohms position. You do not have to manually select a range, because this particular ohm meter has auto ranging. It senses and it knows. And you have a direct digital readout of the resistance value. The large round switch on the analog meter, though, right in the center, is called the range switch. Notice the resistance ohm setting on both of the meters. Okay, so we've got some problems here. 3 circuits, A, B, and C. Why don't you pause the video here and work each one of these and determine what the values are. Notice that in this case we're using the V squared over R relationship to solve for each of the power ratings. When a resistor is used in a circuit, its power rating must be greater than the maximum power that it will have to handle. If a resistor is to dissipate 3/4 of a watt in a circuit, its rating should be at least the next higher value of 1 watt. Ideally, a rating that is approximately twice the actual power should be used when possible. And sometimes that may not happen, but at least get it above the value. Okay, so here we've got another example, 10 volt source, 120 ohm resistor. This is the problem we've already seen where we solved for the 0.833 choosing a 1 watt resistor. The second one, again, we've already seen 10 milliamps of current, 1,000 ohms of resistance gives us 1/10 of a watt, and we chose the 1/8 watt resistor. So as you've learned, when there is sufficient current through a resistor, electrical energy is converted into heat. This heat is caused by collisions of free electrons within the atomic structure of the resistive material. When the collisions occur, heat then is given off, and that's considered a loss. The electron gives up some of its energy then through the material. Okay. In this illustration, it just shows us real quickly, a flow of electrons, and that in each resistor, we're getting an amount of heat dissipation through each resistor. In energy conversion and voltage drops, recall that the voltage equals energy per unit charge. Okay, so volts is equal to the energy divided by charge. And the charge is a property of the electrons. Based on the voltage of the battery, a certain amount of energy is imparted to all of the electrons that flow out of the negative terminal. The same number of electrons flow at each point throughout the circuit, but their energy decreases as it flows through the circuit. Okay, so in this case, we've got the voltage at the left end of R1 is equal to the amount of energy that enters divided by the charge, and the voltage at the right end, R1, is equal to the energy exiting and the charge. The same number of electrons that enters R1 will also exit, and so Q, the charge, remains constant. This decrease in voltage across the resistor due to the loss of energy is what we call a voltage drop. And we're going to do lots of problems where we calculate the drop across resistors in series, in parallel, in series, parallel, and it gets a little more complex with each configuration that we tackle. The voltage at the right end of R1 is less negative or more positive than the voltage at the left end. The voltage drop is indicated by plus and minus signs, and the plus sign implies a less negative or a more positive charge. So we're going to learn more about that, voltages and voltage drops that are due to energy losses. Batteries and power supplies. Recall that power supplies and batteries briefly introduced as types of sources. A power supply is generally defined as an electronic device that converts AC, alternating current, from utility lines to a DC current voltage that virtually all electronic circuits and some transistors require. This is like your wall wart for charging your phone. Batteries are also capable of supplying DC. In fact, many systems such as laptop computers can run from a battery supply or an internal battery or the battery in your phone. Okay, so you've got a couple different types of sources here. Sources that are chemical processes that cause current, and those that are a result of converting AC to DC. Utilities universally have adopted AC for transmitting electricity from the generating station to the user because it can be readily transformed to high voltages or transmission and low voltages for the user N. Okay, there was a big, at the end of the 19th century, late 1890s, there was a big battle between DC and AC being the source, and AC ended up being the one that won out. High voltages are much more efficient and cost-effective to transmit over long distances. It takes a lot more energy, a lot more push to get DC, and it would require more stations to be put up to regenerate the amount of current that you would need. Okay, virtually all electronic systems require stable DC for integrated circuits and other devices to work properly. Generally speaking, your stereo works on DC. It does not work on AC. The power supply converts AC to DC, and that runs your appliance or your device. Power supplies fulfill the function in converting AC to stable DC and are usually built into the product. Okay, and we start from the standard 120 volt source, or 240, or for different applications 440 for higher application requirements. The switch must be set correctly on your device or serious damage can occur. If we look at this diagram, very simply, it's giving you a relationship between the power supply and whatever you're trying to drive. We call it the load here. Power to the load then is equal to the current by the voltage out. You can see the voltage out is taking across the output of the power supply. In this case, we're looking at a triple output power supply that you might find in the lab. You're going to get plenty of practice working with AC and DC power supplies when you work with these devices in the lab. Okay, so do some calculations here. What's the total power delivered by a triple output power supply if the output voltage and current are as follows? So in this case, you can see we've identified source 1, source 2, source 3, and the amount of voltage that it will deliver. So 18 volts at 2 amps, minus 18 volts at 1.5 amps, 5 volts at 1 amps. So to calculate the power delivered from each of those sources, source 1, V1, I1, gives us 36 watts. Source 2, V2, I2, gives us 27 watts. And source 3, V3, I3, gives us 5 watts. Okay, if we wanted to determine what the total power was from all three of those, it's simply a summation. So power 1, power 2, plus power 3 added together gives us a total of 68 watts that this triple output power supply is able to deliver. Okay, efficiency. Efficiency is a quotient relationship, and we look at the output over the input, P out over P in. Efficiency is often expressed as a percentage. For example, if the input power is 100 watts and the output power is 50 watts, we're going to take those two values. The units watts will disappear because they cancel out, and we're going to multiply it times 100, and it gives us a 50% efficiency. All electronic power supplies require that the power be put into them. Okay, for example, an electronic power supply generally uses AC power from the wall outlet as its input. Its output usually is a regulated DC voltage. You're going to learn more about that down the line. The output power is always less than the input power because some of the total power must be used internally to operate the power supply circuitry. And as I said before, there will be losses due to heat. The thing to remember is there's no magic pill here. Everything has some loss. Everything is going to have to give up a little to get a little. So there's no free lunch, as my electronic engineering professors used to say. In circuits, there is no free lunch. This internal power distribution is normally called power loss. The output power then is the initial power minus the power loss. So the output then will be the input minus any loss that occurs. And like I said, that loss can be calculated any number of ways. I squared R loss. Remember, that's power. High efficiency means that very little power is dissipated in the power supply, and there is a higher proportion of output power for a given input power. Okay, an example here of calculating the efficiency: 20 watts out, 25 watts in. We've got 0.8, so that's an 80% efficiency. So that's not too bad. So there's our relationships. Again, put these in your notebook, keep track of them, use them, learn how to use them, become familiar with efficiency. Ampere hours on batteries. Typically, this is a good lesson to understanding your automobile battery. Batteries convert stored chemical energy to electrical energy. And you need to know then, how long is your battery going to last? How much, what they call cranking power. The ampere hour rating determines the length of time a battery can deliver a certain amount of current at the rated voltage. In your car, believe it or not, it takes a lot of current to deliver to your starter to start that engine, to turn that whole thing over. And so you may open up the door and notice you've got lights, but you go to crank it and you get click, 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 click. There's not enough energy left for your ampere hours. It cannot deliver. So if we look at an example here, how many hours can a battery deliver? 2 amps if it's rated at 70 ampere hours. So 70 ampere hours is equal to 2 amps times an unknown number of hours that we're going to calculate for. So let's move our terms around. We're going to move the x to the left, the 70 to the right, and we are going to solve for x. 70 ampere hours divided by 2 amps gives us 35 hours. That's a pretty healthy battery. Okay, so 35 hours of delivering current to the circuit. Okay, so there it is again. Again, work it, get used to it, understand it. Ampere hour ratings of batteries. Certain battery delivers 10 amps for 6 hours. What's its ampere hour rating? The ampere hour rating is the current times the number of hours. We get 60 ampere hours for the battery. Okay, power and energy. You're all experts now. Thank you.